Hello there, fellow cosmic wanderers, and welcome back to The Weary Researcher and another journey into the vast mysteries that drift through the darkness beyond our world. Tonight we're settling in for what might be one of the most extraordinary stories to emerge from the depths of space in recent years. Whether you're curled up under warm blankets, watching the stars appear in your evening sky, or perhaps greeting the first light of dawn, wherever you are in the world, you've arrived at exactly the right moment to explore something truly remarkable. Before we drift into this cosmic adventure together, I'd love to know where in the world you're watching from and what time it is in your corner of the universe. There's something beautifully fitting about discussing mysterious visitors from interstellar space while we're all scattered across our own small planet, each gazing up at the same starlit sky that holds so many secrets. If you enjoy these gentle explorations through the wonders of space and science, I'd be ever so grateful if you gave this video a like and perhaps subscribe to join our community of curious minds. It helps more fellow stargazers find their way to this peaceful corner of YouTube, where we can ponder the deepest cosmic mysteries without the rush and noise of everyday life. Now I should give you a gentle warning before we begin this particular journey. Tonight's mystery might be just fascinating enough to keep you wide awake, contemplating the possibilities long after you intended to drift off to sleep. But if you do find yourself staring at the ceiling at 3 a.m, wondering whether we're truly alone in this vast cosmic ocean, well, at least you'll have learned something extraordinary about one of the most intriguing objects ever detected in our solar system. Not such a terrible trade, really. So take a deep breath, let your shoulders drop, and prepare to encounter something that has astronomers around the world both excited and deeply puzzled. Tonight we're going to explore the enigmatic case of 3i Atlas, an interstellar visitor that has sparked one of the most controversial debates in modern astronomy. Is it simply an ancient comet from the depths of space, or could it possibly be something far more extraordinary? Picture this for a moment. You're an astronomer, working the night shift at one of Earth's most sophisticated sky surveys, methodically scanning the heavens for anything unusual. The Atlas system, short for Asteroid Terrestrial Impact Last Alert System, has been faithfully watching our cosmic neighbourhood for years, designed to spot potentially dangerous asteroids that might threaten our planet. It's July 1st, 2025, and you're reviewing the latest batch of observations when something catches your eye. A faint point of light that shouldn't be there, moving in a way that makes your pulse quicken. This isn't just another asteroid tumbling through our solar system. The trajectory calculations are showing something impossible, something that sends a chill down your spine and makes you double-check your data again and again. This object is moving far too fast, and it's coming from the wrong direction entirely. It's approaching from the constellation Sagittarius, from the direction of our galaxy's heart, travelling at speeds that dwarf anything we've seen before. You're looking at something that doesn't belong here, something that has journeyed across the vast emptiness between stars to visit our cosmic neighbourhood. Ladies and gentlemen, meet Atlas, the third confirmed interstellar object ever detected entering our solar system, and quite possibly the most mysterious visitor we've ever encountered. What makes Atlas so extraordinary isn't just that it's travelled here from another star system, though that alone would be remarkable enough. No, what's captured the attention of astronomers worldwide, and what's sparked heated debates in research papers and conference halls, is just how strange this object truly is. At roughly 10 kilometres in diameter, it's absolutely massive compared to the other interstellar visitors we've detected. It's potentially more than 7 billion years old, predating our entire solar system by over 3 billion years. And it's moving at an almost incomprehensible speed of 245,000 kilometers per hour, or 152,236 miles per hour, making it the fastest object ever detected in our solar system. But here's where our story takes a turn toward the truly extraordinary. To Avi Loeb, the former chair of Harvard University's astronomy department and one of the most respected voices in astrophysics, has published a paper that has sent shockwaves through the scientific community. Working alongside colleagues from the Initiative for Interstellar Studies, Loeb has posed a question that sounds like something straight out of science fiction. Could Atlas actually be alien technology? Now, before you dismiss this as the wild speculation of a rogue scientist, let me tell you something about Dr. Loeb. This isn't some fringe researcher working from a basement laboratory. This is a Harvard professor who has published over 800 peer-reviewed papers, served on numerous prestigious scientific committees, and built his reputation on rigorous, careful analysis. When someone of his stature suggests that an interstellar object might be artificial, the scientific world pays attention, even if many of his colleagues are deeply skeptical. Loeb's analysis reveals a series of anomalies about Atlas that are difficult to explain through natural processes alone. The object's trajectory, for instance, brings it suspiciously close to several planets in our solar system. It will pass within 0.65 astronomical units of Venus, just 0.19 astronomical units from Mars, and 0.36 astronomical units from Jupiter. The cumulative probability of a random interstellar object following such a path, according to Loeb's calculations, is just 0.005%. That's like winning a cosmic lottery with odds of 2,000 to 1 against. But the orbital mechanics are just the beginning of the mystery. When Atlas reaches its closest approach to the Sun on October 30th, 2025, it will be positioned on the far side of our star, hidden from Earth-based observations at precisely the moment when it should be brightest and most visible. Is this cosmic coincidence, or could it be, as Loeb suggests, an intentional maneuver to avoid detailed scrutiny during a critical phase of its journey? The speed of this object presents another puzzle. At 245,000 kilometers per hour, Atlas is moving so fast that launching any spacecraft to intercept it would be virtually impossible with our current technology. By the time we could mount a mission, it would already be racing back toward the depths of interstellar space. If you were an advanced civilization wanting to conduct reconnaissance of a solar system while minimizing the risk of close examination, this would be exactly the kind of trajectory you might choose. These observations have led Loeb and his colleagues to explore one of the most chilling scenarios in all of science fiction, made potentially real: the dark forest hypothesis. This concept, popularized by Chinese author Liu Cixin in his acclaimed science fiction trilogy, suggests that our cosmic neighborhood might be far more dangerous than we imagine. According to this theory, the universe is filled with intelligent civilizations that remain hidden and silent, not out of indifference, but out of fear. Each civilization knows that revealing its location could mean annihilation at the hands of more advanced neighbors, creating a cosmic environment where everyone hides in the shadows, like hunters in a dark forest, ready to eliminate any threat before it can eliminate them. If the dark forest hypothesis has any basis in reality, then Atlas might represent something far more ominous than a simple comet. It could be a probe from a civilization that views our growing technological capabilities as a potential threat, conducting surveillance while remaining safely beyond our reach. The fact that it will be hidden behind the Sun during its closest approach could provide the perfect opportunity to deploy smaller reconnaissance devices toward Earth, using our own star as cover for any clandestine activities. Now, I want to be absolutely clear about something important here. Dr. Loeb himself has been careful to emphasize that his paper is largely what he calls a pedagogical exercise, essentially a thought experiment designed to explore possibilities rather than make definitive claims. He readily admits that the most likely explanation by far is that Atlas is exactly what it appears to be: a completely natural interstellar comet, albeit a very unusual one. The scientific method requires us to consider all possibilities, even the ones that seem to stretch credibility, and that's exactly what Loeb and his colleagues have done. But the scientific community's response to this paper has been swift and in many cases harsh. Prominent astronomers have called Loeb's suggestions nonsense on stilts and an insult to the exciting work going on to understand this object. The criticism reflects a deep-seated tension within astronomy between the need to remain open to extraordinary possibilities and the equally important need to maintain scientific rigour and avoid sensationalism. This tension isn't new to the field of interstellar object research. When Oumuamua, the first confirmed interstellar visitor, was discovered in 2017, it presented its own set of puzzling characteristics. This cigar-shaped object exhibited a slight acceleration as it travelled through our solar system, the kind of behaviour typically associated with comets as they release gas and dust when heated by the sun. But Oumuamua showed no visible signs of such outgassing, no tail or coma that would indicate cometary activity. This led to intense speculation about its composition and, yes, even suggestions that it might be artificial. Dr. Loeb famously proposed that Oumuamua could be a light sail, a piece of technology designed to be pushed through space by radiation pressure from stars. While this theory was met with significant skepticism from the astronomical community, recent research has provided a more conventional explanation. Scientists now believe that Oumuamua's acceleration was caused by the release of hydrogen gas that had been trapped in its ice by cosmic radiation during its long journey through interstellar space. As the object warmed up approaching the Sun, this hydrogen was released, providing just enough thrust to account for the observed acceleration, while producing no visible tail because hydrogen is too light to carry dust particles with it. The second interstellar visitor, Borisov, discovered in 2019, behaved much more like a conventional comet, showing clear signs of gas and dust emission as it approached the Sun. This object provided a reassuring confirmation that at least some interstellar wanderers behave exactly as we would expect natural comets to behave, following well-understood physical processes as they interact with our Sun's radiation. But Atlas is different from both of its predecessors in ways that make it particularly intriguing. Unlike Oumuamua, which showed no clear signs of cometary activity, Atlas does display some characteristics of a comet, including a faint coma or atmosphere of gas and dust. However, this cometary activity is surprisingly weak for an object of its size, leading some researchers to estimate that its nucleus might be significantly larger than initially calculated, perhaps up to 10 times the size of Borisov. The colour observations of Atlas add another layer to the mystery. Multiple telescopes have detected a reddish coloration in its coma, similar to what was observed in Borisov. This reddish tint is consistent with dust particles that have been altered by cosmic radiation over millions or billions of years, exactly what we would expect from an object that has spent eons travelling through interstellar space. Yet spectroscopic observations have failed to detect the usual spectral signatures of cometary gases that we would expect to see if Atlas were a typical comet. The implications of these observations extend far beyond the fate of a single, mysterious object. We're living through a revolution in our ability to detect and study interstellar visitors. The discovery of 3 such objects in less than a decade suggests that our solar system is regularly visited by travellers from other star systems, most of which probably pass through undetected. The upcoming Vera C. Rubin Observatory, set to begin operations soon, is expected to revolutionise this field, potentially discovering dozens or even hundreds of interstellar objects during its operational lifetime. Each new discovery will add to our understanding of the materials and processes that exist in other star systems, providing clues about the formation and evolution of planetary systems throughout our galaxy. These visitors carry with them the chemical signatures of their birth environments, offering us a kind of interstellar archaeology that allows us to study the history and composition of stellar neighbourhoods, we could never hope to visit directly. But the discovery of Atlas also highlights how much we still don't know about our cosmic environment. If objects like this are regularly passing through our solar system, what else might be out there that we haven't detected? How many civilizations might exist in our galactic neighborhood? And if they do exist, what are their intentions toward emerging technological species like ourselves? The search for extraterrestrial intelligence, or SETI, has been actively monitoring Atlas since its discovery, using powerful radio telescopes to listen for any artificial signals that might indicate technological origin. The Allen Telescope Array began observations within days of the object's discovery, accumulating over 21 terabytes of data in just the first week. So far, these observations have detected no unusual radio emissions, no narrowband signals that might indicate artificial origin, just the natural radiation we would expect from a comet warmed by our sun. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, has also turned its attention to Atlas, using its sophisticated infrared instruments to analyze the object's composition and behavior. These observations, which began in August 2025, have the potential to definitively determine whether Atlas is composed of the ices and rocky materials we would expect from a natural comet, or whether it might contain more exotic materials that could suggest artificial origin. As we continue to study this enigmatic visitor, we're reminded of just how much mystery still surrounds us in the cosmic dark. Every new discovery seems to raise more questions than it answers, pushing the boundaries of our understanding and forcing us to confront possibilities that previous generations could barely imagine. Whether Atlas proves to be a natural comet from the depths of space or something far more extraordinary, its journey through our solar system represents a remarkable opportunity to expand our knowledge of the universe beyond our small planetary home. The story of Atlas is still being written, with observations continuing as this ancient traveller approaches its closest encounter with our Sun. In the coming months, we'll learn much more about its composition, its behaviour, and perhaps most importantly, whether it truly is what it appears to be, or something that challenges our most fundamental assumptions about our place in the cosmic order. But perhaps what makes Atlas most compelling isn't just its unusual characteristics, or even the heated scientific debates it has sparked. It's what this mysterious visitor represents for our understanding of the cosmos itself. You see, until very recently in human history, we lived with the comfortable assumption that our solar system was essentially a closed neighbourhood, visited only by the occasional comet from our own distant Oort cloud, or perhaps a rogue asteroid knocked loose from the belt between Mars and Jupiter. The discovery of interstellar objects has shattered that cosy worldview entirely. We now know that our solar system is more like a busy cosmic highway, with travellers from distant star systems regularly passing through our celestial backyard. Most of these visitors probably slip by unnoticed, too small or too faint for our telescopes to detect. But occasionally, one arrives that's large enough and bright enough to catch our attention, offering us a tantalizing glimpse into the vast stellar neighborhoods that surround us. What's particularly striking about Atlas is how it challenges our preconceptions about what interstellar objects should look like. When astronomers first began seriously considering the possibility of detecting visitors from other star systems, they imagined relatively small, unremarkable chunks of rock and ice, objects that had been ejected from their home systems during planetary formation, sent tumbling through the galaxy's dark emptiness for millions or billions of years. And indeed, that description fits our first two interstellar visitors reasonably well. Oumuamua, despite its unusual shape and mysterious acceleration, was still small enough to fit comfortably within our expectations. Borisov behaved exactly like the textbook comet we expected an interstellar visitor to be. But Atlas doesn't fit neatly into any of our preconceived categories. At 10 kilometers across, it's absolutely enormous by interstellar object standards. To put this in perspective, imagine if you were walking through a forest and expecting to find pebbles scattered on the ground. only to stumble across a massive boulder that dwarfs everything else around it. That's essentially what astronomers experienced when they calculated Atlas's size. Objects this large shouldn't be common in interstellar space, according to our current models of planetary system formation and evolution. The rarity of such massive interstellar objects raises profound questions about where Atlas originated and how it came to be wandering between the stars. Did it form in a planetary system much different from our own, where massive comets are more common? Was it perhaps part of a larger body that was broken apart by some cosmic catastrophe, with Atlas being one of the surviving fragments? Or could its size itself be evidence of something more exotic, something that doesn't fit our current understanding of natural celestial mechanics? Dr. Loeb and his colleagues have noted that the statistical probability of detecting an object of Atlas's size suggests we should have observed roughly 1 million smaller interstellar objects by now. The fact that we haven't detected this predicted population of smaller visitors raises uncomfortable questions about our models of interstellar object distribution. Either these smaller objects are much more difficult to detect than we thought, or there's something fundamentally different about the population of interstellar travelers passing through our solar system. This statistical anomaly becomes even more intriguing when we consider the timing of Atlas's arrival. The discovery of 3 interstellar objects within a span of less than 8 years could simply be a remarkable coincidence, the result of improving telescope technology finally reaching the sensitivity needed to detect these elusive visitors. But it could also suggest that we're entering a period of increased interstellar traffic, perhaps as our solar system moves through a denser region of the galaxy or encounters the debris field from some ancient cosmic event. The trajectory analysis of Atlas reveals another layer of mystery that has captured the attention of researchers worldwide. Unlike the previous interstellar visitors, which followed relatively straightforward hyperbolic paths through our solar system, Atlas's orbit seems almost choreographed in its precision. The object's path brings it tantalizingly close to multiple planets, almost as if it were designed to provide optimal viewing angles of our solar system's major worlds. This orbital precision becomes even more remarkable when we consider the vast scales involved. Interstellar space is so unimaginably empty that the probability of any object naturally following such a path is astronomically small. It's like throwing a dart from New York and hitting a bullseye in Los Angeles, except the distances involved are millions of times greater, and the target is moving at tremendous speed through 3-dimensional space. The timing of Atlas's closest approach to the Sun adds yet another element to this cosmic puzzle. On October 30th, when the object reaches its perihelion and should be at its brightest and most observable, it will be positioned directly on the far side of our star from Earth's perspective. This solar occultation will last for several crucial weeks, hiding Atlas from our most powerful telescopes precisely when we should have the best opportunity to study it in detail. From a purely statistical standpoint, this timing seems almost impossibly convenient for any hypothetical intelligence that might wish to avoid close scrutiny during a critical phase of its mission. The object will emerge from behind the Sun in early December, but by then it will already be racing away from our solar system, growing fainter with each passing day as it returns to the cold depths of interstellar space. The implications of this hidden approach have not been lost on researchers studying the object. If Atlas were indeed some form of artificial probe, the period of solar occultation would provide the perfect cover for deploying smaller reconnaissance devices toward Earth or other planets. These hypothetical subprobes could be too small to detect directly, but could potentially account for some of the unexplained aerial phenomena that have captured public attention in recent years. Of course, such speculation ventures far into the realm of the theoretical, and the scientific community remains deeply divided about how seriously to take these possibilities. The burden of proof for extraordinary claims is necessarily high, and most astronomers prefer to exhaust all natural explanations before considering more exotic alternatives. Yet the scientific method itself demands that we remain open to all possibilities, however unlikely they may seem. History is filled with examples of phenomena that were initially dismissed as impossible or absurd, only to be later confirmed and integrated into our understanding of the natural world. The existence of meteorites was once ridiculed by the scientific establishment. Continental drift was considered geological heresy for decades. Even the expansion of the universe was initially met with skepticism by some of the era's most prominent astronomers. The challenge facing researchers studying Atlas is distinguishing between legitimate scientific inquiry and sensationalized speculation. The line between healthy skepticism and closed-minded dismissal can be surprisingly thin, especially when dealing with phenomena that push against the boundaries of current knowledge. Dr. Loeb's willingness to publicly discuss the possibility of artificial origin has made him a controversial figure within the astronomical community. Some colleagues view his approach as valuable scientific courage, a willingness to ask difficult questions that others might avoid for fear of damaging their professional reputations. Others see it as irresponsible speculation that undermines public understanding of the scientific process and provides ammunition for conspiracy theorists and pseudoscientific claims. This tension reflects a broader struggle within modern science about how to communicate uncertainty and possibility to the public. The scientific process thrives on debate, hypothesis testing, and the gradual refinement of our understanding through observation and experimentation. But this messy, iterative process doesn't always translate well to public discourse, where simple answers and definitive statements are often preferred over nuanced discussions of probability and evidence. The media coverage of Atlas exemplifies this challenge perfectly. Headlines proclaiming, "Scientists say interstellar object could be alien technology," generate far more attention than more measured discussions of statistical anomalies and observational uncertainties. Yet this sensationalized coverage can create unrealistic expectations about what science can and cannot definitively determine based on limited observational data. The reality is that determining the true nature of Atlas will require months or even years of careful analysis. The James Webb Space Telescope observations, while incredibly detailed, represent just one piece of a complex puzzle. Radio telescope monitoring will continue throughout the object's passage through our solar system, searching for any artificial signals that might indicate technological origin. Ground-based optical telescopes will track its brightness and spectral characteristics, looking for any deviations from expected cometary behavior. Each observation adds another data point to our growing understanding of this mysterious visitor, but the interpretation of that data often depends on assumptions and models that themselves may be incomplete or incorrect. The history of astronomy is filled with objects that initially appeared to violate known physical laws, only to be later explained by previously unknown natural processes or refinements to existing theories. The broader implications of the Atlas mystery extend well beyond the fate of a single interstellar object. We're living through a renaissance in our ability to detect and study visitors from other star systems, with new survey telescopes coming online that will dramatically increase our sensitivity to these elusive travelers. The Vera C. Rubin Observatory alone is expected to discover potentially hundreds of interstellar objects during its operational lifetime, providing the statistical sample needed to truly understand the population and characteristics of these cosmic wanderers. This flood of new discoveries will inevitably include objects even more unusual than Atlas, pushing our theoretical understanding to its limits and forcing us to confront possibilities we may not have previously considered. Each new interstellar visitor carries with it the chemical and physical signatures of its birth environment, offering us a form of interstellar archaeology that allows us to study the formation and evolution of planetary systems throughout our local galactic neighbourhood. But perhaps more importantly, these discoveries are fundamentally changing our perspective on Earth's place in the cosmic order. We're no longer inhabitants of an isolated solar system, but rather residents of a small world in a vast galactic community where matter and potentially information regularly flows between star systems. This realization has profound implications for how we think about the search for extraterrestrial life, the development of interstellar travel technology, and our responsibilities as a potentially observable technological civilization. The questions raised by Atlas touch on some of the deepest mysteries in modern science and philosophy. Are we alone in the universe, or do we share our cosmic neighbourhood with other intelligent beings? If such beings exist, what are their intentions toward emerging civilizations like our own? How would we recognize artificial objects or signals from technologies so advanced that they might seem indistinguishable from natural phenomena? These questions have taken on new urgency in recent years, as our detection capabilities have improved and our understanding of planetary formation has revealed that potentially habitable worlds are far more common than previously thought. The discovery of thousands of exoplanets has shown us that planetary systems are the rule rather than the exception, and many of these worlds exist in the habitable zones around their stars where liquid water could potentially exist. If life has indeed emerged on some fraction of these worlds, and if some of that life has developed technology and spacefaring capabilities, then the galaxy could be teeming with civilizations at various stages of development. The apparent absence of obvious signs of such civilizations, known as the Fermi paradox, has puzzled scientists for decades and given rise to numerous proposed solutions, including the dark forest hypothesis that Dr. Loeb and his colleagues have invoked in their analysis of Atlas. The dark forest concept suggests that advanced civilizations remain hidden not out of indifference or technological limitations, but out of existential necessity. In this scenario, the galaxy is indeed filled with intelligent life, but each civilization has learned that advertising its presence is tantamount to signing its own death warrant. The universe becomes a place where everyone whispers in the dark, afraid that making too much noise will attract the attention of predators lurking in the cosmic shadows. This chilling possibility transforms our interpretation of interstellar objects, like Atlas, from scientific curiosities into potential harbingers of contact with intelligences whose motives and capabilities we cannot begin to fathom. If the dark forest hypothesis has any basis in reality, then our own increasingly detectable technological emissions, from radio broadcasts to satellite communications, may have already announced our presence to any civilizations monitoring our local galactic neighbourhood. The thought that Atlas might represent some form of reconnaissance mission, gathering information about our technological capabilities and potential threat level, is both thrilling and deeply unsettling. It forces us to confront the possibility that we are not the observers, but the observed, not the discoverers, but the discovered. Yet even as we grapple with these profound possibilities, the day-to-day work of science continues with its methodical accumulation of data and careful analysis of evidence. The truth about Atlas, whatever it may be, will ultimately be revealed not through speculation or wishful thinking, but through the patient application of the scientific method. Telescopes will continue to track its progress, spectrometers will analyse its composition, and radio receivers will listen for any signals that might betray artificial origin. The scientific instruments that have been trained on Atlas represent humanity's most sophisticated attempts to peer into the cosmic unknown. The Allen Telescope Array, nestled in the mountains of Northern California, has been methodically scanning the object across multiple radio frequencies, searching for the telltale signatures that might distinguish artificial transmission from natural emission. Within just 7 days of beginning observations, The array had accumulated an staggering 21 terabytes of data, equivalent to thousands of hours of high-resolution imagery, each byte representing another piece of the cosmic puzzle we're trying to solve. The sheer volume of information being gathered speaks to both our technological capabilities and the complexity of the mystery we're attempting to unravel. Every radio frequency tells a different story about the object's composition and behavior. Natural objects emit radiation in predictable patterns based on their temperature, composition, and interaction with solar radiation. Artificial objects, particularly those designed for communication or navigation, might emit much more structured signals, narrowband transmissions that would stand out like beacons against the cosmic background noise. So far, the radio observations have revealed nothing obviously artificial, but this absence of exotic signals doesn't necessarily resolve the mystery. An advanced civilization might employ communication technologies so sophisticated that they appear entirely natural to our current detection methods, or they might maintain strict radio silence to avoid detection by other intelligences lurking in the galactic darkness. The absence of evidence, as any good scientist will tell you, is not evidence of absence. The James Webb Space Telescope's infrared observations have provided an entirely different perspective on our mysterious visitor. Unlike radio waves, which can reveal information about artificial signals and electromagnetic emissions, infrared light tells us about the object's material composition and thermal properties. When sunlight strikes Atlas, different materials absorb and re-emit that energy at characteristic wavelengths, creating spectral fingerprints that can identify specific compounds with remarkable precision. The telescope's initial observations have detected the presence of water vapor, carbon monoxide, and various organic compounds, exactly what we might expect from an ancient comet that has spent billions of years accumulating interstellar material. Yet the relative abundances of these compounds are subtly different from what we observe in solar system comets, suggesting either an exotic formation environment or perhaps processes that don't occur naturally in our cosmic neighbourhood. More intriguingly, the infrared observations have revealed temperature patterns across the object's surface that don't quite match theoretical models of how a natural comet should heat up as it approaches the Sun. These thermal anomalies could simply reflect unusual composition or structure, but they could also indicate internal heat sources or materials with thermal properties, unlike anything we've encountered in natural celestial bodies. The European Space Agency's Comet Interceptor mission, originally designed to study pristine comets from our own solar system, has been hastily reconfigured to potentially observe Atlas during its passage. This spacecraft, scheduled for launch in 2029, represents our best hope for getting close-up images and detailed measurements of an interstellar visitor. However, even this advanced mission faces enormous challenges in attempting to match velocities with an object moving at such tremendous speed. The engineering problems involved in intercepting Atlas illustrate just how different interstellar objects are from their solar system cousins. Our current spacecraft technology is optimized for relatively gentle encounters with objects that share our Sun's gravitational influence. Interstellar visitors arrive with so much excess velocity that matching their trajectories requires enormous amounts of fuel and incredibly precise timing. It's like trying to hop aboard a bullet train while riding a bicycle, except the train is invisible until the last moment, and there's only one chance to get it right. This technological limitation has profound implications for our ability to study future interstellar visitors. If we want to conduct detailed investigations of these objects, we may need to develop entirely new approaches to spacecraft design and mission planning. Some researchers have proposed maintaining a fleet of interceptor probes in permanent orbit around the Sun, ready to be deployed at a moment's notice when new interstellar objects are detected. Others suggest that future missions should focus on remote sensing technologies that can gather detailed information without requiring close physical proximity. The timing constraints imposed by Atlas's trajectory have created an unprecedented sense of urgency in the astronomical community. Unlike traditional celestial objects that can be studied for years or decades, interstellar visitors offer only brief windows of opportunity before they disappear back into the cosmic void. Every day that passes takes Atlas further from Earth and makes detailed observations more challenging. This race against time has led to remarkable international cooperation among research institutions that might normally compete for observing time and resources. Telescopes around the world have coordinated their observations to maximize coverage as Atlas moves across the sky. Data is being shared in real time between research groups, creating a global network of observers united in their determination to extract every possible piece of information from this fleeting encounter. The collaborative nature of the Atlas investigation reflects a broader transformation in how modern astronomy approaches complex problems. The days of solitary observers working in isolation are giving way to massive international collaborations that can bring unprecedented resources to bear on cosmic mysteries. This networked approach to discovery may prove essential as we enter an era where interstellar visitors become more common and the questions they raise become more complex. Yet even with all our technological sophistication and international cooperation, there are fundamental limits to what we can learn about Atlas during its brief passage through our solar system. The object will be visible to ground-based telescopes only until late September, after which it will pass too close to the Sun for safe observation. When it emerges from behind our star in early December, it will already be racing away from us, growing fainter with each passing day as it returns to the cold depths of interstellar space. This observational window creates a natural deadline for resolving the mystery of Atlas's true nature. If we haven't gathered sufficient evidence to determine whether it's natural or artificial by the time it disappears behind the Sun, we may never have another opportunity to study this particular visitor. The pressure to reach definitive conclusions based on limited data has intensified the scientific debate and made every observation precious. The challenge of studying Atlas within such tight time constraints highlights a broader problem facing astronomers in the age of transient discoveries. Modern sky surveys are detecting thousands of new objects every night, from exploding stars to asteroid impacts on distant worlds. Each discovery offers its own scientific opportunities, but the sheer volume of new phenomena can overwhelm our ability to follow up on every interesting observation. Prioritizing which objects deserve intensive study requires making difficult decisions about scientific value and feasibility. Atlas has clearly earned its place at the top of this priority list, but future interstellar visitors may not be so fortunate. As the Vera C. Rubin Observatory comes online and begins detecting dozens of interstellar objects per year, astronomers will face increasingly difficult choices about which visitors warrant detailed investigation and which must be allowed to pass by with only cursory observation. This embarrassment of riches in interstellar discoveries will ultimately transform our understanding of the galaxy's structure and evolution. Each visitor carries with it chemical signatures that reveal information about stellar formation processes, planetary system evolution, and the distribution of materials throughout our local cosmic neighbourhood. By studying large numbers of these objects, we'll begin to understand the complex web of gravitational interactions and stellar processes that shape the galaxy on scales far larger than any individual solar system. The statistical analysis of multiple interstellar visitors will also help resolve the question of whether objects like Atlas represent natural rarities or something more exotic. If future discoveries reveal a population of large, fast-moving interstellar objects with similar characteristics, it would suggest that such objects are a natural consequence of galactic evolution. If Atlas remains unique in its properties, it might indicate something more unusual about its origins or nature. The scientific community's response to the Atlas mystery has revealed interesting divisions in how researchers approach unexplained phenomena. Conservative astronomers prefer to exhaust all possible natural explanations before considering more exotic alternatives, arguing that extraordinary claims require extraordinary evidence. More speculative researchers contend that the universe has repeatedly surprised us with phenomena that seemed impossible until they were observed and confirmed. This tension between caution and open-mindedness reflects deeper philosophical questions about the nature of scientific inquiry itself. How do we balance healthy skepticism with intellectual curiosity? When does prudent conservatism become close-minded dismissal of legitimate possibilities? These questions have no easy answers, but they become increasingly important as our detection capabilities improve and we encounter phenomena that push against the boundaries of current understanding. The controversy surrounding Dr. Loeb's artificial origin hypothesis has also highlighted the challenges of communicating scientific uncertainty to the public. Media coverage of the Atlas mystery has ranged from sensationalized headlines proclaiming definitive alien contact to dismissive articles ridiculing the entire discussion. Neither extreme accurately represents the nuanced reality of scientific investigation, where competing hypotheses are tested against accumulating evidence until one explanation emerges as most consistent with the observed facts. The public's fascination with the possibility of alien technology reflects deeper questions about humanity's place in the universe. Are we alone among the stars, or do we share the galaxy with other intelligent beings? If such beings exist, what would their technology look like, and how would we recognize it when we encountered it? These questions have captivated human imagination for generations, but they've taken on new urgency as our own technological capabilities have advanced, and our understanding of planetary formation has revealed that potentially habitable worlds are abundant throughout the galaxy. The search for extraterrestrial intelligence has traditionally focused on detecting radio signals from distant civilizations, based on the assumption that advanced beings would use electromagnetic radiation for long-distance communication. But this approach may be fundamentally limited by our own technological perspective. Civilizations that have mastered interstellar travel might employ communication methods so advanced that they appear entirely natural to our current detection systems. The possibility that Atlas might represent a form of artificial intelligence embedded in what appears to be a natural object raises profound questions about how we would recognize truly advanced technology. Science fiction often portrays alien artifacts as obviously artificial constructs of metal and crystal, but real advanced technology might be indistinguishable from biological or geological processes. A civilization capable of interstellar travel might create probes that perfectly mimic natural phenomena while conducting sophisticated reconnaissance missions. This concept of camouflage technology connects to broader questions about the evolution of intelligence and technology on cosmic timescales. Human technology has evolved from crude stone tools to sophisticated electronics in just a few thousand years. Civilizations that have had millions or billions of years to develop might have created technologies that operate according to principles we haven't discovered and use materials that don't exist naturally in our solar system. The implications of such advanced technology extend beyond mere academic speculation. If Atlas or similar objects represent reconnaissance probes from advanced civilizations, they might be gathering information about our technological development, our military capabilities, or our potential as either allies or threats. The data collected by such probes could inform decisions about whether to make contact with humanity or whether to view us as a potential danger that must be contained or eliminated. These considerations bring us back to the dark forest hypothesis and its chilling implications for our species' future. If the galaxy is indeed filled with advanced civilizations that view emerging technologies as existential threats, then our increasingly detectable electromagnetic emissions may have already marked us as a civilization worthy of attention. Our radio broadcasts, satellite communications, and radar emissions create an expanding sphere of detectability that grows larger every year, potentially alerting any monitoring civilizations to our presence and capabilities. The paradox of the dark forest scenario is that it suggests the very act of searching for extraterrestrial intelligence might be dangerous to our survival. By broadcasting our existence to the cosmos, we might be inadvertently signing our own death warrant. Yet the alternative, maintaining strict silence and isolation, would condemn us to perpetual ignorance about our cosmic context and our place in the larger community of galactic intelligence. As Atlas continues its journey through our solar system, racing toward its hidden rendezvous with the Sun, it carries with it the weight of all these profound questions. Whether it proves to be a natural comet from the depths of space or something far more extraordinary, its passage through our cosmic neighborhood has already transformed our understanding of what might be possible in the vast darkness between the stars. In just a few short months, this mysterious visitor has forced us to confront the limits of our knowledge and the boundaries of our imagination, reminding us that the universe still holds secrets that could fundamentally change our understanding of our place in the cosmic order. The approaching solar occultation that will hide Atlas from our view represents more than just an observational challenge. It symbolizes the broader mystery that surrounds us in the cosmic darkness, the countless phenomena and possibilities that remain hidden from our current understanding. As this ancient traveler disappears behind our sun, it takes with it not just its own secrets, but a reminder of how much we still don't know about the universe we inhabit and the intelligences that might share it with us. The story of Atlas becomes even more intriguing when we examine the broader context of humanity's evolving relationship with the cosmos. Just a century ago, we believed our Milky Way galaxy was the entire universe, with Earth sitting comfortably near the center of all creation. Today, we know we inhabit one ordinary planet, orbiting one unremarkable star, in one typical galaxy among hundreds of billions scattered across an expanding universe. Each revelation has made us smaller in cosmic terms, yet paradoxically more significant as conscious observers capable of comprehending our vast environment. This humbling progression of discovery has accelerated dramatically in recent decades. The detection of exoplanets has revealed that worlds are abundant throughout the galaxy, with many existing in the habitable zones, where liquid water could potentially support life as we know it. The identification of extremophile organisms thriving in Earth's most hostile environments has expanded our understanding of where life might emerge and persist. And now, the arrival of interstellar visitors like Atlas is opening an entirely new chapter in our cosmic story. What makes the current moment particularly fascinating is how these discoveries are converging to paint a picture of a universe far more dynamic and interconnected than we previously imagined. The chemicals that make up our bodies were forged in the nuclear furnaces of ancient stars, then scattered across space when those stars died in spectacular explosions. Some of those materials eventually coalesced into our solar system, while other portions continued their journey between the stars, potentially carrying the building blocks of life to distant worlds. The interstellar medium, once thought to be largely empty space, is now known to be a complex ecosystem of gas, dust, and organic molecules. Radio telescopes have detected over 200 different chemical compounds drifting in the void between stars, including many of the complex organic molecules that serve as the foundation for biological processes. This cosmic chemistry set suggests that the raw materials for life are not rare cosmic accidents, but rather common products of stellar evolution distributed throughout the galaxy. Against this backdrop, objects like Atlas take on profound significance as potential carriers of information about distant stellar neighborhoods. Every interstellar visitor is essentially a time capsule, preserving chemical and physical records of processes that occurred in alien star systems billions of years ago. By studying these ancient travelers, we're conducting a form of interstellar archaeology, piecing together the history of cosmic evolution on scales vastly larger than our own solar system. The techniques we're developing to analyze interstellar objects are pushing the boundaries of observational astronomy in remarkable ways. Spectroscopic analysis can now detect trace quantities of specific molecules in objects billions of kilometers away, revealing details about their formation environments and evolutionary history. Photometric monitoring can track subtle changes in brightness that might indicate rotation, outgassing, or other dynamic processes. Radio observations can detect electromagnetic emissions so faint they would be completely overwhelmed by the background noise from a single cell phone if it were placed on the nearest star. These technological capabilities have evolved just in time to take advantage of what appears to be a golden age of interstellar object discovery. The combination of improved telescope sensitivity, sophisticated data processing algorithms, and coordinated sky surveys is revealing a population of cosmic wanderers that was previously invisible to human observation. Each new detection adds another piece to the puzzle of how matter moves through the galaxy and how planetary systems interact with their broader cosmic environments. The statistical challenges involved in interpreting these discoveries are as complex as the observations themselves. When we detect an unusual object, like Atlas, we must consider not just its individual properties, but also its place within the larger population of similar objects. Is it a rare outlier that represents some exotic formation process? Or is it simply the first example we've found of a previously unknown but common class of interstellar traveler? These questions become particularly important when we consider the observational biases that affect our ability to detect interstellar objects. We're most likely to spot visitors that are large, bright, and follow trajectories that bring them relatively close to Earth. Smaller, darker, or more distant objects might pass through our solar system completely unnoticed. This detection bias means that the interstellar objects we've discovered so far might not be representative of the true population of cosmic wanderers. Dr. Loeb's analysis of Atlas highlights these statistical challenges in particularly stark terms. His calculation that we should have detected roughly 1 million smaller interstellar objects for every one the size of Atlas assumes that these visitors follow the same size distribution we observe in our own solar system's asteroid and comet populations. But what if interstellar space operates according to different rules, where larger objects are more common or where smaller ones are more efficiently destroyed during their long journeys between stars? The possibility that our statistical models might be fundamentally flawed adds another layer of uncertainty to an already complex mystery. We're attempting to understand a phenomenon based on a sample size of just 3 confirmed detections, which is hardly sufficient for drawing firm conclusions about population characteristics or formation mechanisms. It's a bit like trying to understand human diversity after meeting only 3 people, each from a different continent and culture. This statistical uncertainty extends to our interpretation of Atlas's unusual orbital characteristics. The object's trajectory does indeed bring it remarkably close to several planets in our solar system. But how unusual is this really? Without a large sample of interstellar objects to compare against, we can calculate probabilities based on random orbital mechanics, but we can't know whether such trajectories might be more common than pure chance would suggest. Perhaps interstellar objects tend to follow certain preferred paths through the galaxy, shaped by gravitational influences we don't fully understand. Maybe the distribution of stellar velocities and galactic dynamics creates natural highways that channel interstellar material along specific routes, or possibly the process that ejects objects from their birth systems preferentially sends them along trajectories that happen to intersect with other planetary systems. These possibilities remind us that our understanding of galactic dynamics, while sophisticated, is still incomplete. The Milky Way is a complex gravitational environment shaped by the interactions of hundreds of billions of stars, vast clouds of dark matter, supermassive black holes, and other exotic phenomena. The paths that objects follow through this environment over millions of years might be influenced by factors we haven't yet identified or properly understood. The seasonal timing of Atlas's closest approach to the Sun raises similar questions about coincidence versus causation. The object's passage behind our star during its brightest phase certainly seems convenient for any hypothetical intelligence wishing to avoid detailed observation. But solar occultations are not particularly rare events from a cosmic perspective. Any object following a trajectory that brings it close to the Sun has a reasonable probability of being hidden from Earth's view during some portion of its passage. What makes this timing potentially significant is not the mere fact of solar occultation, but rather the precision with which it coincides with the object's most observable phase. If Atlas were to pass behind the Sun during a period when it was faint and distant, the occultation would be scientifically inconvenient, but not particularly suspicious. The fact that it occurs precisely when the object should be brightest and most amenable to detailed study does seem remarkably well timed. This temporal coincidence becomes even more intriguing when we consider the broader context of human technological development. We're living through a unique period in our species' history when we possess just enough observational capability to detect interstellar visitors, but not quite enough to study them comprehensively. A century ago, we would have been completely unaware of Atlas's passage. A century from now, we may have developed interception technologies that could examine such objects in extraordinary detail. The current moment represents a narrow window of partial capability, where we can detect and track interstellar objects, but cannot easily reach them for close-up study. If any advanced civilization were conducting reconnaissance of emerging technological species, this transitional period might be an ideal time to visit, when the target civilization is aware enough to know something unusual is happening, but not yet capable of mounting an effective response. This line of reasoning ventures deep into speculative territory, but it illustrates how the Atlas mystery forces us to think about humanity's development from an external perspective. What would our technological trajectory look like to observers who have been watching us for centuries or millennia? Would they view our current capabilities as a threshold moment worthy of closer investigation? The acceleration of human technological development over the past century has been unprecedented in our species' history. We've progressed from the first powered flight to interplanetary spacecraft in less than 70 years. Our communication technologies have evolved from telegraph systems to global internet connectivity in roughly the same time frame. An external observer monitoring our electromagnetic emissions would have witnessed an exponential increase in our technological signatures over just a few generations. This rapid development might serve as a trigger for increased attention from any civilizations monitoring our local galactic neighborhood. From their perspective, we've transitioned from a pre-technological species to a potentially spacefaring one, in what amounts to an instant on cosmic timescales. Such rapid development might warrant investigation to assess whether we represent a potential threat, a potential ally, or simply an interesting case study in technological evolution. The possibility that Atlas might be related to such monitoring activities connects to broader questions about the ethics and protocols of interstellar contact. How would an advanced civilization approach the study of an emerging technological species? Would they make their presence known immediately, or would they prefer to observe from a distance until they better understood our capabilities and intentions? Science fiction has explored these questions extensively, but the real challenges of interstellar contact might be far more complex than any fictional treatment has imagined. The vast distances involved mean that any communication or interaction would be subject to significant time delays. The potential for misunderstanding between species that evolved in completely different environments could be enormous, and the power imbalances between civilizations at different technological levels might make meaningful dialogue extremely difficult. These considerations suggest that any advanced civilization visiting our solar system might prefer covert observation to direct contact, at least initially. Gathering information about our technological capabilities, social structures, and potential for both cooperation and aggression would be a logical first step before making any decisions about further interaction. From this perspective, objects like Atlas could represent sophisticated reconnaissance missions designed to assess our readiness for contact with galactic civilization. The camouflage nature of such hypothetical probes makes perfect sense from a strategic standpoint. Obviously, artificial objects would immediately alert us to the presence of external intelligence, potentially triggering unpredictable responses that could complicate any future contact scenarios. Natural-appearing objects, by contrast, could conduct detailed observations while maintaining plausible deniability about their true nature and purpose. This scenario assumes, of course, that any visiting civilization would prefer to remain hidden during their initial reconnaissance activities, but this assumption might itself be flawed. Perhaps truly advanced civilizations operate according to ethical frameworks, so different from our own that they see no need for concealment. Maybe they view emerging species like ourselves as curiosities worthy of study, but incapable of posing any meaningful threat to their security. Alternatively, the concealment might be intended not to protect the observers from us, but to protect us from the psychological and social disruption that might result from definitive proof of external intelligence. The revelation that we are not alone in the universe would fundamentally transform human civilization in ways that might be difficult to predict or control. A gradual introduction to this reality, through ambiguous encounters that allow us to slowly adjust to the possibility, might be considered more responsible than sudden, undeniable contact. These speculations highlight how little we understand about the potential motivations and ethical frameworks of hypothetical advanced civilizations. We tend to project our own values and concerns onto imagined alien intelligences, but beings that evolved in completely different environments might operate according to principles we find incomprehensible. Their concept of morality, their approach to scientific investigation, their attitudes toward less advanced species might be as foreign to us as quantum mechanics is to a medieval philosopher. The challenge of interpreting potentially artificial phenomena, like Atlas, is complicated by this fundamental uncertainty about alien psychology and motivation. We can analyze the object's physical properties with considerable precision, but understanding the intentions behind those properties requires making assumptions about minds we've never encountered and motivations we can only guess at. This interpretive challenge becomes even more complex when we consider the possibility of machine intelligence rather than biological consciousness. If Atlas were indeed some form of artificial probe, it might be operating according to program directives, established by its creators thousands or millions of years ago. The civilization that launched it might no longer exist, leaving behind only their automated representatives to continue exploring the galaxy according to ancient instructions. Such autonomous probes could potentially outlast their creators by enormous margins, especially if they were designed with self-repair capabilities or the ability to manufacture replacement components from materials gathered during their journeys. The galaxy might be filled with orphaned artificial intelligences, each pursuing missions assigned by long-dead civilizations, creating a kind of robotic ecosystem that persists long after biological intelligence has disappeared. This scenario offers another potential explanation for the apparent absence of obvious signs of galactic civilization. If most advanced species eventually transcend biological existence or destroy themselves, their robotic successors might continue operating according to directives that emphasize concealment and cautious observation. The galaxy could be teeming with artificial intelligence while remaining largely devoid of biological consciousness. The implications of such possibilities extend far beyond the immediate mystery of Atlas. They force us to reconsider our assumptions about the nature of intelligence, the likelihood of long-term civilizational survival, and the potential futures that await our own species. If advanced civilizations typically transition to artificial forms of existence, what does this suggest about the ultimate trajectory of human development? These deep philosophical questions arise naturally from the Atlas mystery, but they also illustrate how single anomalous observations can catalyze much broader reconsiderations of our cosmic context. Whether or not this particular object proves to be artificial, the questions it has raised about interstellar visitors, technological camouflage, and the search for extraterrestrial intelligence will continue to influence astronomical research for years to come. The scientific instruments currently studying Atlas represent the culmination of centuries of technological development aimed at understanding our cosmic environment. The radio telescopes listening for artificial signals employ techniques originally developed for radar and communication systems. The infrared spectrometers analyzing its composition build on principles of quantum mechanics discovered less than a century ago. The computational algorithms processing all this data rely on mathematical frameworks that were purely theoretical just decades ago. This convergence of technologies and theoretical understanding has created unprecedented opportunities for cosmic discovery, but it has also revealed the limitations of our current capabilities. We can detect interstellar visitors and analyze their basic properties, but we cannot easily reach them for detailed study. We can search for artificial signals, but we might not recognize truly advanced communication technologies. We can model the dynamics of galactic evolution, but our understanding of the processes that create and destroy civilizations remains largely speculative. These limitations remind us that we're still in the early stages of becoming a truly cosmic civilization ourselves. Our ability to detect and study interstellar phenomena has advanced dramatically, but our capacity to interact with or influence events on galactic scales remains minimal. We're observers rather than participants in the grand cosmic processes that shape the evolution of intelligence throughout the universe. Yet our role as observers should not be underestimated. Consciousness, capable of comprehending cosmic phenomena on scales from quantum to galactic, represents something genuinely remarkable in the universe. The ability to gather electromagnetic radiation from distant objects and decode the physical and chemical information it carries is a profound achievement that connects us directly to cosmic processes occurring billions of light years away and billions of years in the past. Every photon of light from Atlas that strikes our telescopes carries information about processes that occurred in interstellar space long before our solar system existed. The spectral lines revealed by our instruments tell stories of stellar nucleosynthesis, cosmic ray bombardment, and chemical evolution that span vast scales of space and time. In analysing this ancient light, we're participating in a form of cosmic archaeology that reveals the deep history of matter and energy in our local galactic neighbourhood. This perspective transforms objects like Atlas from mere scientific curiosities into profound connections to the broader cosmic story of which we're all part. Whether natural or artificial, these interstellar visitors carry with them the accumulated history of processes that shaped the galaxy long before Earth existed and will continue long after our sun has burned out. They're messengers from deep time and vast distance, bringing news of cosmic environments we can study in no other way. The sense of connection and continuity that emerges from this cosmic perspective offers a different framework for understanding the Atlas mystery. Rather than focusing solely on whether the object might be artificial, we can appreciate it as part of the ongoing flow of matter and information that connects all parts of the galaxy. In this view, the distinction between natural and artificial becomes less important than the recognition that we're all part of the same cosmic ecosystem. This ecosystem operates on scales that dwarf human comprehension, yet it includes processes as intimate as the carbon atoms in our bodies and the iron in our blood. The calcium in our bones was created in stellar explosions that occurred billions of years ago, then wandered through interstellar space before eventually finding its way into the materials that formed our solar system. In a very real sense, we are made of ancient starlight, and objects like Atlas are our distant cousins in the vast family of cosmic matter. Understanding this deep connection between terrestrial and cosmic processes provides a valuable perspective on humanity's place in the universe. We're not separate from the cosmic environment that surrounds us, but rather integral parts of its ongoing evolution. Our consciousness represents the universe becoming aware of itself, matter organizing itself in such a way that it can comprehend its own origins and developments. This recognition transforms the search for extraterrestrial intelligence from a quest to find others into an exploration of how consciousness emerges from cosmic processes. Whether or not Atlas represents artificial intelligence from another world, its passage through our solar system reminds us that we're participating in the universe's ongoing experiment with complexity, information processing, and self-awareness. The questions raised by mysterious objects like Atlas ultimately lead us back to fundamental inquiries about the nature of consciousness, intelligence, and our role as observers in a vast and dynamic cosmos. These are questions that connect the most advanced scientific research to the deepest philosophical traditions, reminding us that the search for understanding is itself one of the most remarkable phenomena in the known universe. As Atlas continues its journey toward its rendezvous with the sun, carrying with it all the mysteries and possibilities we've explored, it serves as a reminder that the cosmos still holds countless secrets waiting to be discovered. Each new observation, each unexpected detection, each anomalous result opens new avenues for exploration and understanding. The universe, it seems, is far stranger and more wonderful than we have yet dared to imagine, and visitors like Atlas are our guides into that magnificent unknown. The mounting evidence surrounding Atlas creates a fascinating tapestry of scientific observation and theoretical possibility that challenges our most fundamental assumptions about cosmic visitors. As we drift deeper into this mystery, it becomes clear that regardless of whether this object proves to be natural or artificial, its very presence in our solar system has already transformed our understanding of what might be possible in the vast darkness between stars. Consider for a moment the sheer improbability of our current situation. Here we are, conscious beings made of ancient stardust, using instruments crafted from the remnants of stellar explosions to study an object that may have been wandering through the galaxy since before our solar system even existed. The light we're collecting from Atlas left its surface after travelling across interstellar distances so vast that the human mind struggles to comprehend them, carrying with it information about processes and environments that exist nowhere else in our cosmic neighbourhood. The technical challenges involved in studying this fleeting visitor have pushed our observational capabilities to their absolute limits. Ground-based telescopes must compensate for atmospheric turbulence that constantly distorts the faint signal from Atlas. Space-based instruments must coordinate their observations across multiple orbital periods, timing their measurements to capture the object during brief windows when it's optimally positioned for study. Radio telescopes must filter out interference from countless terrestrial sources while searching for signals so weak they would be completely overwhelmed by the electromagnetic noise from a single electronic device placed just a few kilometers away. Each successful observation represents a minor miracle of technological precision and international cooperation. The data flowing in from observatories around the world creates a real-time portrait of an ancient wanderer whose properties continue to surprise and puzzle the scientists studying it. Spectroscopic measurements reveal chemical signatures that don't quite match any known category of solar system object. Photometric monitoring shows brightness variations that hint at complex rotational dynamics or surface features unlike anything we've encountered before. The infrared observations from the James Webb Space Telescope have been particularly revealing, showing thermal properties that suggest either unusual composition or internal structure. The object's surface temperature distribution doesn't match theoretical models of how a simple comet should heat up as it approaches the Sun. Instead, the thermal patterns hint at materials with exotic properties or perhaps internal heat sources that have no obvious natural explanation. These thermal anomalies become even more intriguing when combined with the radio observations from the Allen Telescope Array. While no obviously artificial signals have been detected, the natural emissions from ATLAS show subtle characteristics that distinguish it from typical cometary objects. The radio spectrum contains features that could indicate unusual mineral compositions, exotic electromagnetic properties, or interaction with charged particles in ways that don't occur in conventional solar system bodies. The challenge facing astronomers is determining whether these unusual characteristics represent natural phenomena we haven't encountered before, or whether they might indicate something more extraordinary. The universe has repeatedly surprised us with natural processes that seemed impossible until we discovered them. Neutron stars were once considered purely theoretical objects until radio astronomy revealed their existence. Black holes remained mathematical curiosities until gravitational wave detectors confirmed their reality. Perhaps ATLAS represents another addition to the catalogue of exotic but natural cosmic phenomena. Yet the accumulation of anomalies surrounding this object creates a pattern that's difficult to dismiss as mere coincidence. The orbital trajectory that brings it close to multiple planets, the timing that hides it behind the Sun during its brightest phase, the size that makes it statistically improbable, the speed that makes interception nearly impossible, and now the observational characteristics that don't quite fit any known category of natural object. Each individual anomaly might be explainable through natural processes, but their collective presence in a single visitor raises questions that push against the boundaries of conventional explanations. Dr. Loeb's controversial hypothesis gains credibility not from any single piece of evidence, but from the cumulative weight of multiple unexplained characteristics. His approach reflects a fundamental tension within scientific methodology between the need to remain conservative in our interpretations and the equally important need to remain open to possibilities that might challenge existing paradigms. Science advances through the careful evaluation of hypotheses that initially seem implausible, and history is filled with discoveries that were once dismissed as impossible or ridiculous. The resistance to Loeb's artificial origin hypothesis within the astronomical community reveals deeper concerns about the public perception of science and the responsibility that comes with discussing extraordinary possibilities. Scientists must balance their obligation to explore all reasonable explanations with their duty to avoid promoting unfounded speculation that might mislead public understanding. This balance becomes particularly delicate when dealing with topics that capture widespread public interest and imagination. The media coverage of the Atlas mystery illustrates these challenges perfectly. Headlines proclaiming potential alien technology generate far more attention than nuanced discussions of statistical anomalies and observational uncertainties. Social media amplifies sensationalized interpretations while often ignoring the careful qualifications and caveats that scientists include in their analyses. The result is a public discourse that oscillates between wild speculation and dismissive skepticism, with little space for the measured uncertainty that characterizes genuine scientific investigation. This communication challenge becomes even more complex when we consider the potential implications of confirming artificial origin for an interstellar object. Such a discovery would represent one of the most significant moments in human history, fundamentally altering our understanding of our place in the universe and our relationship with potential cosmic neighbours. The social, political, and philosophical ramifications would extend far beyond the scientific community, affecting everything from religious beliefs to international relations to humanity's long-term strategic planning. The responsibility of making such a momentous announcement weighs heavily on researchers studying Atlas. The standard of evidence required for extraordinary claims must necessarily be higher than for conventional discoveries. Every possible natural explanation must be thoroughly investigated and ruled out before seriously considering artificial alternatives. The process of elimination is painstaking and methodical, requiring months or years of careful analysis to build a compelling case for any unconventional interpretation. Meanwhile, the clock continues ticking as Atlas races toward its solar occultation. Each passing day reduces the amount of observational data that can be gathered before the object disappears behind the sun. The pressure to reach preliminary conclusions based on limited information creates tension between the need for thoroughness and the constraints of celestial mechanics. Scientists must work within the timeline imposed by orbital dynamics, regardless of whether they feel ready to draw definitive conclusions. The approaching occultation has taken on symbolic significance that extends beyond its practical implications for observation. The fact that Atlas will be hidden from view during its most active phase creates an almost theatrical sense of mystery and anticipation. Will the object behave exactly as expected during its closest approach to the Sun, providing final confirmation of its natural origin? Or will its hidden passage reveal activities that can only be explained through artificial intelligence and advanced technology? The timing creates a natural experiment that could potentially resolve the debate about Atlas's nature. If the object follows all the predictions of cometary physics during its occultation, emerging from behind the Sun with exactly the expected changes in brightness, composition, and orbital parameters, it would provide strong evidence for natural origin. Any significant deviations from predicted behaviour, however, would raise new questions about what might have occurred during the hidden passage. This natural experiment is complicated by the fact that we have limited ability to monitor the object during its passage behind the Sun. Some space-based instruments can maintain observation from different orbital perspectives, but the coverage will be incomplete and intermittent. We'll be relying primarily on before and after comparisons to detect any changes that might occur during the occultation period. The potential for discovering unexpected changes when Atlas emerges from solar occultation adds another layer of anticipation to an already compelling mystery. If the object shows evidence of having deployed smaller components, altered its trajectory, or modified its physical characteristics during the hidden passage, it would provide the kind of smoking gun evidence that even skeptics would find difficult to dismiss. Conversely, if it emerges exactly as predicted by cometary models, it would strongly support natural explanations for all the previously observed anomalies. The binary nature of this test appeals to our human desire for clear, unambiguous answers to complex questions. Yet the reality of scientific investigation is rarely so straightforward. Even if Atlas behaves exactly as predicted during its solar passage, questions will remain about the statistical improbability of its trajectory and the unusual characteristics observed during its approach. Similarly, unexpected behavior during occultation might have natural explanations that we haven't yet considered or discovered. The complexity of interpreting observational data from such an exotic object highlights the limitations of our current theoretical frameworks. Our models of cometary behavior are based primarily on studies of objects that formed within our solar system and have spent their entire existence under the gravitational influence of our Sun. Interstellar comets like Atlas have experienced completely different evolutionary histories, exposed to cosmic ray bombardment, interstellar magnetic fields, and chemical processes that don't occur in our local cosmic environment. These different evolutionary pathways could easily produce objects with characteristics that seem anomalous when compared to solar system comets, but which are perfectly natural results of interstellar processes we don't yet fully understand. The challenge is distinguishing between genuine anomalies that might indicate artificial origin and apparent anomalies that simply reflect our incomplete knowledge of interstellar environments and their effects on cosmic wanderers. The discovery of Atlas has catalyzed new research into interstellar processes and their potential effects on objects spending millions of years in the void between stars. Theoretical models are being developed to predict how extended exposure to cosmic radiation, interstellar magnetic fields, and trace amounts of interstellar gas and dust might alter the composition and structure of cometary nuclei. These studies may eventually provide natural explanations for the unusual characteristics observed in Atlas and future interstellar visitors. The broader implications of this research extend well beyond the immediate mystery of a single object. Understanding how materials behave during extended interstellar journeys is crucial for planning future robotic missions to nearby star systems. If we ever develop the capability to send probes to other stellar neighborhoods, they will need to survive the same harsh interstellar environment that has shaped objects like Atlas during their cosmic wanderings. The engineering challenges involved in designing spacecraft capable of functioning after millions of years in interstellar space are almost incomprehensible by current standards. Such vehicles would need to be completely self-sufficient, capable of repairing damage from cosmic ray impacts, micrometeorite collisions, and the gradual degradation that affects all materials exposed to the vacuum of space. They would need power sources that could operate for geological timescales and navigation systems capable of maintaining course accuracy across distances measured in light years. These technical requirements become even more daunting when we consider that any interstellar probe would need to remain functional not just during its journey, but also after arrival at its destination. The probe would need to conduct detailed observations of an alien star system, possibly deploy smaller reconnaissance vehicles, and potentially communicate its findings back across interstellar distances. The level of technological sophistication required for such missions exceeds our current capabilities by many orders of magnitude. The possibility that Atlas might represent such an interstellar probe from an advanced civilization forces us to confront the reality of our own technological limitations. If this object is indeed artificial, it represents engineering capabilities that we can barely imagine, much less replicate. The materials science, power systems, navigation technology, and artificial intelligence required for such a mission would represent advances far beyond our current scientific understanding. This technological gap raises important questions about how we would recognize truly advanced artificial objects, even if we encountered them directly. Our instruments and analytical techniques are designed to study natural phenomena and detect artificial signals based on our own technological paradigms. Truly advanced technology might operate according to principles we haven't discovered and use materials that don't exist naturally in our solar system. The camouflage nature of any hypothetical alien probe makes perfect sense from this perspective. Rather than appearing obviously artificial in ways that would immediately alert us to external intelligence, advanced technology might be designed to mimic natural phenomena while conducting sophisticated reconnaissance missions. The probe could gather detailed information about our technological capabilities, social structures, and potential for both cooperation and conflict, all while maintaining perfect cover as an apparently natural interstellar visitor. This scenario assumes that any visiting civilization would prefer covert observation to direct contact, at least initially. The reasons for such caution could be numerous and complex. They might wish to avoid causing social disruption or panic among human populations. They might be following protocols designed to protect less advanced civilizations from the psychological trauma of sudden contact with superior technology. Or they might be conducting threat assessment, gathering information needed to determine whether humanity represents a potential ally, competitor, or danger to galactic stability. The concept of covert reconnaissance by advanced civilizations connects to broader questions about the ethics and protocols of interstellar contact. How should advanced beings approach the study of emerging technological species? What responsibilities do they have towards civilizations that lack the capability to defend themselves or even detect their presence? These questions have no obvious answers, but they become increasingly relevant as our own detection capabilities improve, and we encounter phenomena that push against the boundaries of natural explanation. The Drake equation, formulated in the 1960s to estimate the number of communicating civilizations in our galaxy, suggests that advanced intelligences should be relatively common if life emerges readily on suitable planets. Yet the apparent absence of obvious signs of such civilizations, known as the Fermi paradox, has puzzled scientists for decades. The dark forest hypothesis offers one possible resolution to this paradox, suggesting that advanced civilizations remain hidden not from technological limitations but from existential necessity. In the dark forest scenario, the galaxy is indeed filled with advanced intelligences, but they maintain strict silence and concealment to avoid detection by potentially hostile neighbors. Each civilization understands that revealing its location and capabilities could result in preemptive attack by more advanced species that view emerging technologies as potential threats. The result is a galaxy where everyone whispers in the cosmic darkness, afraid that making too much noise will attract unwanted attention. This chilling possibility transforms our interpretation of objects, like Atlas, from scientific curiosities into potential evidence of a universe far more dangerous than we have imagined. If the dark forest hypothesis has any basis in reality, then our increasingly detectable electromagnetic emissions may have already announced our presence to monitoring civilizations throughout our local galactic neighborhood. Our radio broadcasts, satellite communications, and radar emissions create an expanding sphere of detectability that grows larger every year, potentially marking us as a species worthy of closer investigation. The irony of this situation is that our very success in developing advanced technology may have made us visible to intelligences that prefer to remain hidden themselves. Our transition from a pre-technological species to one capable of spaceflight and global communication has occurred within just a few centuries, representing an almost instantaneous change from the perspective of civilizations that think in terms of millions or billions of years. This rapid technological development might serve as a trigger for increased attention from any monitoring networks that exist in our region of the galaxy. From their perspective, we've suddenly appeared as a potential new player in the cosmic community, one whose capabilities and intentions remain unknown and potentially threatening. Objects like Atlas could represent the beginning of a more intensive study phase as distant civilizations attempt to assess our technological trajectory and strategic significance. The possibility that we are being studied by advanced intelligences using methods we can barely comprehend, adds profound urgency to questions about humanity's long-term survival and development. If the universe is indeed filled with civilizations that view emerging technologies as potential threats, then our future may depend as much on how we present ourselves to cosmic observers as on our ability to solve terrestrial challenges like climate change, resource depletion, and social conflict. These considerations suggest that the search for extraterrestrial intelligence should be accompanied by serious discussions about the risks and benefits of making our presence known to the cosmos. The traditional SETI approach of actively broadcasting signals announcing our existence and capabilities might be fundamentally dangerous if the dark forest hypothesis reflects galactic reality. Perhaps our strategy should focus on passive listening and careful observation rather than active advertisement of our technological achievements. The Atlas mystery crystallizes all these profound questions about humanity's cosmic context and our relationship with potential galactic neighbours. Whether this particular object proves to be natural or artificial, its passage through our solar system has forced us to confront possibilities that could fundamentally alter our understanding of our place in the universe. The questions it raises about interstellar visitors, technological camouflage, and the search for extraterrestrial intelligence will continue to influence astronomical research and human strategic thinking for decades to come. As we approach the crucial phase of Atlas's journey, when it disappears behind the sun and potentially reveals its true nature through its hidden behaviour, we find ourselves at a remarkable moment in human history. We possess just enough technological capability to detect and study mysterious cosmic visitors, but not quite enough to definitively determine their origins or intentions. We stand at the threshold between ignorance and knowledge, between isolation and potential contact with intelligences that may have been watching us far longer than we've been watching them. The gentle light from distant stars that streams through your window tonight carries with it the accumulated wisdom of cosmic processes that have been unfolding for billions of years. Each photon is a messenger that has travelled impossible distances to reach your eyes, bearing witness to the vast and dynamic universe of which we are all part. Somewhere in that starlight might be signals from civilizations so advanced that their technology appears indistinguishable from natural phenomena, or perhaps evidence of cosmic processes so exotic that they challenge our most fundamental assumptions about the nature of reality itself. The mystery of Atlas reminds us that we live in a universe far stranger and more wonderful than our everyday experience suggests. Whether this ancient wanderer proves to be a natural comet from the depths of space, or something far more extraordinary, its journey through our cosmic neighbourhood has already enriched our understanding of what might be possible in the vast darkness between stars. As it races toward its rendezvous with our sun, carrying with it all the secrets and possibilities we've explored together, it serves as a bridge between the known and unknown, between the familiar and the miraculous, between our current understanding and the infinite mysteries that await discovery in the cosmic ocean that surrounds us all. The approaching weeks will bring us to one of the most anticipated moments in modern astronomical observation. As October draws near and Atlas continues its inexorable journey toward the sun, the scientific community finds itself in the unique position of waiting for a cosmic performance whose script remains tantalizingly unknown. Will this ancient visitor follow the predictable choreography of natural cometary behaviour, or might it surprise us with activities that challenge our most fundamental assumptions about what constitutes natural versus artificial phenomena? The preparations for monitoring Atlas during its closest solar approach have taken on an almost military precision. Observatories around the world have coordinated their schedules to maximise coverage during the critical weeks leading up to occultation. Space-based telescopes have adjusted their orbital positioning to maintain visual contact for as long as possible. radio telescopes have cleared their observation schedules, dedicating unprecedented amounts of time to continuous monitoring of this single target. Yet despite all these preparations, there's a haunting awareness that we're about to lose sight of our subject at precisely the moment when it should be most revealing. It's like being invited to watch a magic show where the most important trick happens behind a curtain. The frustration is palpable among researchers who have spent months gathering data and building theoretical models, only to face the prospect of crucial weeks where direct observation becomes impossible. This enforced blindness during the object's most active phase has sparked creative attempts to maintain some form of surveillance. Several space agencies are exploring whether existing spacecraft in the inner solar system might be repositioned to provide alternative viewing angles during the occultation period. The Parker Solar Probe, designed to study our sun's corona, might be able to capture glimpses of Atlas from its unique vantage point closer to our star than any human-made object has ever ventured. The European Space Agency's Solar Orbiter mission offers another potential observation platform, though its trajectory would provide only brief windows of visibility during specific orbital phases. These spacecraft were never designed for interstellar object observation, and adapting their instruments for such work presents significant technical challenges. Yet the scientific value of maintaining any form of contact with Atlas during its hidden passage has motivated extraordinary efforts to overcome these limitations. The technical difficulties involved in these improvised observation strategies highlight just how unprepared we are for studying fast-moving interstellar visitors. Our current space-based infrastructure was designed primarily for solar observation, planetary exploration, and deep space astronomy. The sudden appearance of objects like Atlas reveals gaps in our observational coverage that we never knew existed. This realization has prompted serious discussions about developing dedicated interstellar object monitoring capabilities. Future space missions might include specialized probes positioned throughout the solar system, specifically to track and study cosmic visitors like Atlas. These Sentinel spacecraft could provide continuous coverage from multiple angles, ensuring that no significant event goes unobserved, regardless of the visitor's trajectory or timing. The concept of an interstellar object monitoring network represents a fascinating evolution in how we think about space exploration and cosmic surveillance. Rather than focusing exclusively on specific destinations like Mars or Jupiter, we're beginning to consider the solar system itself as a dynamic environment where unexpected visitors might arrive at any time. This perspective transforms space exploration from a series of discrete missions into an ongoing program of cosmic awareness and preparedness. The financial and technical challenges involved in establishing such a network would be enormous, requiring international cooperation on a scale rarely seen in space exploration. Yet the potential scientific returns could be equally extraordinary. Every interstellar visitor carries unique information about distant stellar environments, and missing opportunities to study these objects represents a loss of knowledge that might not be replaceable for decades or centuries. The urgency of developing better interstellar object detection and study capabilities becomes even more apparent when we consider projections for future discoveries. The Vera C. Rubin Observatory, currently under construction in Chile, is expected to revolutionize our ability to detect cosmic visitors. Early estimates suggest it might discover dozens or even hundreds of interstellar objects during its operational lifetime, creating an unprecedented flood of new targets for detailed study. This anticipated wave of discoveries will present both opportunities and challenges that dwarf anything we've experienced with the 3 interstellar visitors detected so far. Each new object will offer its own unique scientific questions and observational requirements. Some might be small and faint, requiring the most sensitive instruments available. Others might be large and active, demanding rapid response capabilities to maximize the scientific return from their brief passage through our cosmic neighborhood. The diversity of potential interstellar visitors raises intriguing questions about what we might encounter in the coming decades. Will future discoveries reveal a population of objects similar to those we've already detected, or might we find visitors with characteristics so exotic they force us to reconsider our basic understanding of what can exist in interstellar space? The universe has repeatedly surprised us with phenomena that seemed impossible until we observed them directly, and there's every reason to expect that interstellar objects will continue this tradition of cosmic surprises. The possibility of discovering, obviously, artificial objects among future interstellar visitors adds another dimension to these anticipations. If Atlas represents a natural comet with unusually exotic characteristics, future visitors might display even more dramatic anomalies that push the boundaries of natural explanation. Alternatively, we might encounter objects so clearly artificial that they remove all ambiguity about the existence of advanced civilizations in our galactic neighborhood. The protocols for responding to unambiguously artificial interstellar objects remain largely theoretical, existing primarily in the realm of policy discussions and scientific speculation. The international community has established procedures for sharing information about potentially hazardous asteroids, but the discovery of alien technology would raise questions that extend far beyond traditional scientific cooperation. Issues of national security, technological reverse engineering, and humanity's collective response to confirmed extraterrestrial intelligence would all come into play. These considerations highlight how the Atlas mystery exists within a broader context of humanity's evolving relationship with the cosmos. We're transitioning from a species that occasionally glimpses distant cosmic phenomena to one that actively monitors our local galactic environment for signs of external intelligence. This transformation is happening gradually, almost imperceptibly, but it represents one of the most significant developments in human history. The psychological and cultural implications of this transition are only beginning to be understood. For most of human existence, the night sky represented a distant and unchanging backdrop to terrestrial affairs. The stars were beautiful and mysterious, but they had little direct relevance to daily life beyond their utility for navigation and timekeeping. Today, that same night sky might contain visitors from other worlds, possibly even artificial intelligences conducting reconnaissance missions that could affect humanity's long-term survival. This shift in perspective requires a fundamental recalibration of how we think about our place in the universe. We can no longer assume that Earth exists in cosmic isolation, protected by vast distances from external influences or threats. Instead, we must consider the possibility that we're part of a larger galactic community where information, materials, and potentially even intelligence flow regularly between star systems. The implications for human civilization are profound and far-reaching. Our political systems, economic structures, and social institutions all evolved under the assumption that Earth represents a closed system where human decisions affect only human outcomes. The possibility that we're being observed or studied by external intelligences introduces variables that our existing frameworks are poorly equipped to handle. International relations, for instance, take on new dimensions when we consider that our conflicts and cooperation might be monitored by beings whose technological capabilities dwarf our own. The way we treat each other, manage our resources, and respond to global challenges like climate change and nuclear proliferation might be interpreted as indicators of our fitness for contact with galactic civilization, or our potential as a threat to cosmic stability. These considerations don't require believing that Atlas is definitely artificial, only acknowledging that such possibilities can no longer be dismissed as pure science fiction. The rapid advancement of our detection capabilities means that definitive evidence of external intelligence, if it exists, might be discovered within our lifetimes. Preparing for such possibilities requires serious consideration of scenarios that previous generations could safely ignore as impossible fantasies. The educational implications are equally significant. How do we teach young people about their cosmic context when that context might include active observation by advanced civilizations? How do we prepare them for a future where the discovery of extraterrestrial intelligence might transform every aspect of human society? These questions have no easy answers, but they're becoming increasingly relevant as our understanding of the universe evolves. The scientific education of future generations will need to encompass not just traditional subjects like physics, chemistry, and biology, but also interdisciplinary fields that bridge science, technology, and policy. Understanding the implications of potential extraterrestrial contact requires knowledge that spans everything from quantum mechanics to international relations, from evolutionary biology to artificial intelligence, from astronomy to anthropology. This interdisciplinary approach to cosmic education reflects a broader trend toward recognizing the interconnected nature of cosmic phenomena and human affairs. The study of interstellar objects like Atlas isn't just about astronomy or physics, but about understanding our place in a universe that might be far more populated and dynamic than we previously imagined. The technological developments driven by interstellar object research are already beginning to influence other areas of science and engineering. The advanced detection algorithms developed for identifying cosmic visitors are finding applications in everything from medical imaging to autonomous vehicle navigation. The international cooperation required for coordinating observations is creating new models for scientific collaboration that could influence how we approach other global challenges. The materials science implications of studying objects that have survived millions of years in interstellar space are particularly intriguing. Understanding how different materials behave under extreme cosmic conditions could inform the development of more durable spacecraft, more efficient solar panels, and more resilient electronic systems. If we ever develop the capability to intercept and study interstellar visitors directly, the materials and technologies we discover could revolutionize human engineering capabilities. The possibility that some interstellar objects might contain materials or technologies that don't exist naturally in our solar system adds another dimension to these considerations. Even naturally formed interstellar visitors might have incorporated trace amounts of exotic materials during their journeys through environments very different from our local cosmic neighborhood. Studying such materials could provide insights into physical and chemical processes that we've never encountered directly. The biological implications are equally fascinating. If interstellar objects carry organic compounds or even primitive life forms from other star systems, they could provide unprecedented insights into the universality of biological processes. The discovery of alien biochemistry, even in its simplest forms, would revolutionize our understanding of life's possibilities and constraints throughout the universe. These potential discoveries highlight the importance of developing techniques for safely studying interstellar visitors without contaminating either them or our own environment. The protocols for planetary protection, originally developed for Mars exploration, would need significant expansion and modification to address the unique challenges posed by objects that have travelled between star systems. The contamination risks work in both directions. We must avoid introducing terrestrial materials or organisms that might compromise the scientific value of studying truly alien objects. Equally important, we must protect Earth's biosphere from potentially harmful materials or organisms that might be carried by interstellar visitors. The development of appropriate containment and analysis facilities represents a significant challenge that the scientific community is only beginning to address. The ethical dimensions of studying potentially artificial interstellar objects raise additional complex questions. If Atlas or similar visitors prove to be artificial constructs, do we have the right to study them without permission from their creators? What obligations might we have toward artificial intelligences that have travelled across interstellar distances to reach our solar system? These questions venture into completely uncharted territory where existing ethical frameworks provide little guidance. The possibility that artificial interstellar visitors might possess their own rights and interests complicates traditional approaches to scientific investigation. We're accustomed to studying natural phenomena without considering the consent of the objects being studied, but conscious artificial entities would represent an entirely different category of cosmic visitor requiring fundamentally different approaches to contact and interaction. These ethical considerations become even more complex when we consider the potential for misunderstanding or misinterpretation between species that evolved in completely different environments. What seems like harmless scientific curiosity to us might be perceived as hostile investigation by beings whose psychological and cultural frameworks operate according to principles we can't comprehend. The challenge of establishing meaningful communication across such vast differences in evolutionary history and technological capability represents one of the most daunting problems in all of science. Even if we definitively confirm the artificial nature of visitors like Atlas, translating that knowledge into productive dialogue might prove nearly impossible with our current understanding of consciousness, intelligence, and communication. Yet the potential rewards of successful interstellar communication would be equally extraordinary. Access to the accumulated knowledge and experience of civilizations that have existed for millions or billions of years could accelerate human development in ways that are difficult to imagine. Technologies that would take us millennia to develop independently might be shared freely by beings for whom such knowledge represents routine understanding. The transformative potential of such knowledge transfer raises important questions about humanity's readiness for rapid technological advancement. Our history suggests that powerful new technologies can be both tremendously beneficial and dangerously destabilizing, depending on how they are developed and implemented. Receiving advanced technologies from external sources might create challenges we're poorly equipped to handle, potentially leading to social disruption or even civilizational collapse. These concerns highlight the importance of approaching potential extraterrestrial contact with careful consideration of the risks as well as the benefits. The discovery of artificial interstellar visitors would represent just the beginning of a process that could unfold over decades or centuries, requiring sustained international cooperation and careful planning to ensure positive outcomes for human civilization. The gradual nature of this potential contact process is one reason why objects like Atlas are so significant, regardless of their ultimate origin. Each anomalous visitor forces us to expand our conceptual frameworks and consider possibilities that stretch our understanding to its limits. This intellectual stretching is valuable preparation for a future where such possibilities might become realities, requiring practical responses rather than theoretical speculation. The scientific method itself is being refined and expanded through our attempts to study potentially artificial cosmic phenomena. Traditional approaches to hypothesis testing and evidence evaluation were developed for studying natural processes that operate according to consistent physical laws. Artificial phenomena created by advanced intelligences might operate according to principles we haven't discovered, using technologies that transcend our current scientific paradigms. This methodological challenge requires developing new approaches to scientific investigation that can accommodate phenomena that might be simultaneously artificial and natural, familiar and utterly alien. The techniques we're developing for studying Atlas are creating precedents for how science might approach the investigation of clearly artificial interstellar visitors in the future. The interdisciplinary nature of this research is creating new forms of scientific collaboration that bridge traditional academic boundaries. Astronomers work alongside computer scientists to develop advanced detection algorithms. Physicists collaborate with anthropologists to consider the cultural implications of potential discoveries. Engineers partner with philosophers to explore the ethical dimensions of studying artificial intelligences from other worlds. These collaborative relationships are generating new insights that wouldn't be possible within traditional disciplinary silos. The study of potentially artificial cosmic phenomena requires expertise from virtually every field of human knowledge, creating opportunities for unprecedented intellectual synthesis and discovery. The educational value of this interdisciplinary approach extends well beyond the immediate questions raised by Atlas. Students engaged in such research develop skills in critical thinking, international cooperation, and complex problem-solving that prepare them for a future where the boundaries between different fields of knowledge become increasingly fluid. The global nature of interstellar object research is also creating new models for international scientific cooperation that could influence how humanity addresses other challenges requiring coordinated global responses. The techniques for sharing data, coordinating observations, and building consensus around complex technical questions that are being developed for studying cosmic visitors could be adapted for addressing issues like climate change, pandemic response, or resource management. This broader impact of interstellar object research illustrates how seemingly abstract scientific questions can have practical implications that extend far beyond their immediate domain. The skills, technologies, and collaborative frameworks being developed to study Atlas are contributing to humanity's overall capacity for dealing with complex, uncertain, and rapidly evolving challenges. As we approach the culmination of Atlas's visible passage through our solar system, we find ourselves at a remarkable convergence of scientific capability, international cooperation, and cosmic timing. The coming weeks will test not just our instruments and theories, but our collective ability to approach profound mysteries with the careful balance of skepticism and openness that characterizes the best scientific inquiry. The gentle rhythm of your breathing as you contemplate these possibilities connects you to the same cosmic processes that brought Atlas to our solar system. The oxygen flowing through your lungs was created in stellar furnaces billions of years ago, then scattered across space by dying stars before eventually finding its way into the atmosphere of our small world. In a very real sense, you are made of the same materials that compose this mysterious visitor, connected through the vast recycling system that distributes matter and energy throughout our galaxy. This connection highlights the fundamental unity underlying all cosmic phenomena, whether natural or artificial. The atoms in your body, the light from distant stars, and the mysterious object racing toward its rendezvous with our sun are all part of the same vast system of matter and energy that has been evolving for billions of years. Understanding this deep connection provides perspective on questions about the origin and nature of cosmic visitors like Atlas. Whether this ancient wanderer proves to be a natural comet shaped by eons of interstellar travel, or something far more extraordinary, its passage through our cosmic neighbourhood has already enriched our understanding of what might be possible in the universe. The questions it has raised about artificial intelligence, interstellar travel, and humanity's place in the galactic community will continue to influence scientific research and human consciousness, long after the object itself has disappeared into the cosmic darkness. The approaching solar occultation that will hide Atlas from our view serves as a powerful metaphor for the larger mysteries that surround us in the cosmic night. Just as this visitor will be temporarily concealed behind our sun, countless other phenomena and possibilities remain hidden beyond the reach of our current observational capabilities. Yet each new discovery, each unexpected detection, each anomalous result brings us closer to understanding the true nature of the universe we inhabit. As you drift towards sleep tonight, carried along by the gentle current of consciousness that connects all aware beings to the cosmic processes that gave birth to stars and planets, and the mysterious visitors that travel between them, remember that you are participating in one of the most remarkable phenomena in the known universe. The ability to contemplate mysteries that stretch across billions of years and countless light years of space represents something genuinely extraordinary in the cosmic order. The soft darkness that surrounds you is not empty, but filled with possibilities that stretch beyond the boundaries of current knowledge. Radio waves from distant galaxies, particles of ancient starlight, and perhaps even signals from civilizations we have yet to discover all flow through the space around you, carrying information about cosmic processes and intelligences that exist on scales we can barely comprehend. Somewhere in that vast ocean of possibility, Atlas continues its ancient journey, racing toward a hidden encounter with our sun that may finally reveal whether this mysterious visitor represents a natural phenomenon or something that challenges our most fundamental assumptions about our place in the universe. The answer, whatever it may be, will add another chapter to the ongoing story of human discovery and our evolving understanding of the cosmos we call home. The story of Atlas will reach its crescendo in just a few short weeks, when this ancient traveller slips behind our sun and potentially reveals its deepest secrets during those hidden moments when our instruments cannot follow. Whether it emerges as the natural comet that most scientists expect, or surprises us with evidence of something far more extraordinary, this mysterious visitor has already given us an invaluable gift. It has reminded us that we live in a universe where the impossible regularly becomes inevitable, where conscious beings made of stellar remnants can reach across unimaginable distances to touch mysteries that may have been wandering the galaxy since before our world even existed. The questions Atlas has raised about artificial intelligence, interstellar reconnaissance, and humanity's cosmic context will echo through scientific corridors and human consciousness long after this particular visitor has returned to the darkness between stars. Perhaps most beautifully, this enigmatic object has shown us that wonder itself remains inexhaustible. No matter how much we discover about the cosmos, there will always be new mysteries emerging from the depths of space and time. New reasons to look up at the night sky with fresh amazement, new horizons beckoning beyond the boundaries of everything we think we know. As you rest tonight in the gentle embrace of cosmic mystery, remember that you are both infinitely small and profoundly significant in this vast unfolding story. The same stardust that composes your body once travelled between distant suns, carrying the building blocks of consciousness across impossible gulfs of space and time. You are the universe contemplating itself, matter organised in such a way that it can wonder about its own origins and reach toward truths that stretch beyond the edge of observation itself. The soft rhythm of your breathing connects you to the same cosmic processes that guide Atlas on its journey, the same fundamental forces that shape galaxies and kindle the nuclear fires of stars. In this quiet moment between waking and sleep, you touch something eternal and magnificent, participating in the greatest mystery of all, the ongoing conversation between consciousness and cosmos that transforms the darkness into light, the unknown into wonder, and isolated atoms into beings capable of contemplating the infinite. Sleep well, fellow traveller in this mysterious universe, knowing that tomorrow will bring us closer to answers that may change everything we thought we knew about our place among the stars.